The keynote speak is entitled Edge Clouds, Architecture and Deployment Model. Professor Rana is a part of Computer Science and Informatics Department in Cardiff University. He leads the research group in complex system, and his research interest includes intelligent system, high-performance distributed computing, and cybersecurity. He is also editor and chairs for many IEEE, ACM, high-impacted and prestigious journals and conferences. Let us welcome Professor Omer Rana from in ICTCS.
Okay, so I hope you can hear me okay. So Bismillah ar-Rahman ar-Rahim. So it's great to be here. Thank you for inviting by Professor Abajan. So, and it's great to be in Oman. So I will keep this to half an hour, 25 minutes, just so that you have a chance for questions. I'll skip over some slides. So essentially, research is a team sport, right? So you work with lots of other people. There's a whole bunch of other people that have collaborated on this work. And if you like what you hear, you can follow my Twitter account. So, okay, so essentially, just building this picture, what happens today is that we have a number of devices which are trying to analyze data by sending data to the cloud. So you can have wearable devices such as Fitbit, Nike Fuel. You can have in-car networks, as we heard this morning, or you can have medical accelerators or equipment. And each of these devices has different data rates. So you can have megabits, for example, with megabits per second, processing power of gigaflops to about 1 watt of power usage, right up to high-end devices, which can consume up to gigawatts in terms of power usage. And also you can have about 1 terabit per second data rates. So what happens today is that this data from these devices goes into a cloud infrastructure, and the processing takes place in the cloud, right? So, however, the question is that in many cases, many of these devices which are shipping data to the cloud don't need to ship all this data, right? Because, for example, if I have a surveillance camera in this room, in many cases, you don't need to ship all the raw data to the cloud because nothing happens, right? So your camera is looking at something, but no activity actually takes place. So the question is, and this is the focus of this talk, is how can we stretch the cloud towards the network edge? And what we would have normally done in the cloud, can we do it at these edge devices? And that is a summary of the talk. So these edge devices have increasing capability and capacity. Transferring the data through our public networks can become a bottleneck. And security and privacy concerns are also constrained that in many cases, you don't want to move your private data to the cloud because you don't want to share your private key with a cloud provider. In many ways, some people do not trust the cloud provider. So not all edge data is essential, as I mentioned in the video case. So the objectives are, so the focus of the research that is driving this work is to understand when and what data can be analyzed close to where it's generated rather than pushing it into the cloud. So what can be done at the edge? And how can we use techniques from approximate computing as a trade-off between quality, time, and resources used? And how can we leverage resources closer to the edge, closer to the user, in order to improve our quality of service and our time of processing? So especially if you're generating a video stream and you want real-time kind of characteristics, your network latency may become so high that doing processing in the cloud doesn't make sense, right? So just to give you an example, again, building on the talk by Professor Murphy this morning, this is a slide from Intel. Intel says that an autonomous vehicle is going to generate 4,000 gigabytes of data per day, right? So that's per day. So think of your mobile phone, right? What is your data plan, right? Is it 24 gigabytes per month, 30 gigabytes per month, 100 gigabytes per month? So basically, every vehicle is a data center on wheels. And so you can think of LiDAR data at about 10 to 70 megabytes, GPS data, sonar data, and so on. So essentially, pushing this data into a cloud, it doesn't make sense. Right? So the question is, what can we do at the edge? And that's the focus. So the summary is we need to rethink our data center architectures in order to basically consider what can be done at the edge and how do we combine what is at the edge with the data center? How do we move away from centralized solutions to more peer-to-peer clouds? And how do we support service provisioning and orchestration at the network edge? So that's basically the crux of the research that's being done in this area, right? So In computer science, we are great at coming up with new terminology, right? Everyone wants to invent their own buzzword. So in this area, there's a lot of buzzwords, right? So we have things like cloud of things. We have fog computing, an initial idea generated by Cisco called cloudlets. And so both of these ideas are to extend computing to the edges of the network to overcome latency constraints. So the idea is that if I push data to the cloud, what can I do at the network edge? And many telco vendors are also benefiting from this. So real-world pervasive systems are also benefiting from this. So essentially, all the telecom companies who've invested in base stations and mobile switching stations and so on can now do computation also in addition to just handling your mobile phone traffic. So for example, there's a lot of work in something called mobile and task offloading. Basically, the idea here is that if I have something running on my mobile phone has limited battery and compute capability. So what mobile offloading does is it takes what you do on your phone and pushes it into the cloud so that you can reduce the power consumption, the battery, the compute consumption of your device. So what we are interested in edge computing is the opposite of that. So the question is, when these mobile devices become more intelligent, how do I shift what I was normally have done in the cloud back into the mobile device in order to reduce the constraints on the cloud? So it's also referred to as reverse mobile offloading. So again, there's a whole bunch of stuff with this. An example of this is Akamai. So if you watch BBC or CNN or any of these other streamed video content, more likely than not, you will use Akamai. Akamai is a content distribution network which handles web traffic at 25 terabits per second with about 2 trillion daily transactions per day. So 2 trillion daily transactions per day. And what they do is they don't use clouds, but they use an edge server ensemble. So what they do is rather than have very complex data centers, what Akamai does is it uses an ensemble of 175,000 servers. And this is a very interesting statistic that almost 85% of the world's population is one hop to an Akamai server. Because your last hop, right, your last hop from your last router to the user is a bottleneck. It's not the data center, because the data center already has very high connectivity. It's the last hop connectivity, the last mile connectivity, which is what Akamai is supposed to do. So what we are saying is, how can we take the Akamai model and don't just use it for data content, but for everything, for compute, for video processing, for security. So how can we apply this new architectural model for all kinds of computations? So that's really the focus of this work. So I'll skip this part in timing. So the European Telecom Standards Institute, that's what ETSI stands for, has come up with this idea of mobile edge computing architecture using network function virtualization. And they have a whole bunch of standardization approaches currently being built. So really, edge clouds is where telecom meets distributed computing and high performance computing. So all the work that's been done in 5G networks, so all this stuff on 5G networks like the evolved packet core, long-term evolution, Cloud RAN, which is cloud-based radio access networks, and it's a combination of these two, of edge computing and mobile networks, where essentially most of these developments are taking place. Okay, so you can read up more on this. So essentially the question is, where is the edge, right? Does the edge sit, is the edge inside the devices that we own, like your sensors, your mobile phone, or does the device actually stretch right up to the intermediate routers? So the idea now is that with techniques like open network function virtualization and software-defined networks, the network also is becoming programmable. So OpenFlow was a standard from Hewlett-Packard, which is allowing, and this is a net FPGA board, which allows you to program your network from the user perspective. So what happens is that as your data moves through the network, you can run services directly in the network. So what you do is you separate the data path and the control path. So the data flows in one direction, and the control path is the software that you run on that data, and that control path can be dynamically programmed. So again, your clouds are no longer here, no longer in the data center. Everything is now a cloud, right from the point of data capture through your network, through your data center. So your cloud stretches through all these three layers. Okay, so that's the idea. So we came up with this technique called osmotic computing. We wanted to create our own buzzword, right? So osmotic computing says that if I have a cloud data center and an edge device, how do I move services between the cloud data center and the edge device? Very much like a fluid flow. So it's like the concept of a fluid flow. You have this concept that when the cloud data center becomes congested, you push some of the services to the edge. And when the edge has lower capability, or you have security constraints, you move these services back to the cloud data center. So we have this migration of microservices from the edge to the data center and in reverse using containers like Docker. So we use lightweight containers to move microservices between the data center and the edge. And this could be triggered by a whole bunch of events. So for example, if your latency, your network latency from your edge to the data center becomes very high, you can move your services closer to the user. So this migration could be triggered through latency events. It could also be triggered through security events, right? So we have a paper here that you can read more about. So certain services, for example, are not moved. So we have security services which stay in place. So very much like the concept of osmosis in solution. So you have a solution with a lower gradient and a higher gradient. You move molecules around from one gradient to another. It's essentially moving electronic services between the edge and the cloud, utilizing this concept of osmotic ideas. So microservices can be both management services, which manage the network, and they can be user-owned services like data analytics, which can then run data processing directly at the edge, for example, data filtering, and then do some data mining in the cloud. You can couple these two together using this kind of osmotic model. And this aligns with work on 5G networks and evolved packet core as a service and user-owned network management functions that the network community is trying to propagate. Okay, so you can read up more about this. Just to put all of this into perspective, I'll show you an example of a scenario that shows some of these concepts in practice, right? And I have about another couple of minutes, so I'm timing my talk, so I'll make sure. Okay, so here's an example. Suppose we take a building like this, right? Suppose a building, so this is energy management in built environments. Suppose we take a building, and a building can be equipped with sensors that reads different properties of the building. So normally, for example, I can read my energy profile, I can read how much lighting is being consumed, I can read the number of people in the room. So we can have a whole bunch of sensors that make readings of the building at about 15 to 30-minute intervals. So we often don't need a higher frequency than that. So what we do is we take this real-time data and we pass it into a high-performance, a package called Energy Plus from the US Department of Energy. And what this does is it's used to model the energy flow within a building. So Energy Plus is a HPC, so you need to run it on a compute cluster in order to run this within a certain deadline. So the sensors feed a real-time execution of Energy Plus. And we take the output of Energy Plus, and then we control the building. We can change set points on the building. We can change your heating, ventilation, air conditioning system. We can have actuators in the building that can then take data from Energy Plus and then feeds the HVAC system. Okay, so this is part of a European project called Sporty. What Sporty does is it looks at sports facilities across Europe, and it tries to optimize the energy usage in these sports facilities. So here's an example. So so sports facilities are a different special kind of building. They're not a normal building because they have a swimming pool which can have water evaporation from here, which can change your energy and energy use. So this is the kind of facility in Rome. It's a sports facility in Rome. And this building is equipped by sensors from a German company called Schneider Electric. So we have sensors from Schneider. And what happens is these sensors monitor different characteristics of a building. So you have indoor temperature, indoor humidity, outdoor temperature, supply airflow, inlet temperature. And this data goes into a building automation server also provided by Schneider. So Schneider has a automation server and a building management server. And this data is then passed into a cloud, and the cloud runs Energy Plus, right? So what you're doing is you're taking the data from these raw sensors and you're feeding a cloud simulation. So the idea is that new data arrives every 15 minutes, so you have to complete your simulation within 15 minutes, because otherwise new data will have arrived. right? So just to pull this more, so these are the actual sensors. I'll just show you the sensors. So we have occupancy sensor, indoor temperature, water temperature, indoor humidity, air temperature, supplied airflow. We have thermal energy and electrical energy, carbon concentration, because it's a chlorine in the air, because it's a sports facility. These are the actual sensors, and these are the data protocols. So we have Modbus, we have RS485, DNP, which is another protocol. So we actually take the data from these sensors and feed them into this energy, this kind of automation server. So here's an example of what happens. So our data comes from the building. It's fed by the sensors into a gateway node, which is the building automation server. Using web services and HTTP call, it goes into a master node. And from the master node, it goes into a compute cluster. So we run the simulation on the compute cluster. And after the simulation completes, it goes and basically changes the actuation on the building. Right? So what we can show here is that we can run a simulation of, we can run 72 concurrent energy plus tasks in 1 hour. Right? So you can see the task completion rate. And we can do it on a single cloud, or we can do it on a federated cloud composed of multiple resources. Right? So we can compare it to, you have a 1 hour deadline versus a 1 hour, 30-minute deadline, and you can change your cloud architecture as a way to support this kind of execution of these tasks. So this is an example of running this Energy Plus simulation on a cloud with 3 nodes versus a cloud with 6 nodes within a certain deadline. Right? So that's the example of how you would perform this operation from these sensors. However, the interesting part is, right, that from the sensors to the cloud, we have a network. Right? So there is a network. So what happens is when data goes from here to here, it passes into a network. So the question is, right, that how can I use my network? So when the data goes from here to here, can I partially process the data before it hits the cloud? Right? So the question is that as the data is moving through the network, can I do some partial processing within the network before you, so rather than do all the processing in the cloud, can I also use the capability in my programmable network in order to be able to process this raw data? And that's what we've looked at in Edge Cloud. So what we do is we try to formulate this problem as an optimization problem. So I have 15 minutes, 14 minutes. So what we do is we can say that as the data migrates from here to here, can I try to convert this into, and so we do this in this way. So consider a job, an energy plus job, which consists of k tasks. Right? So these are the tasks that I want to use. And what I want to do is I want to complete these tasks within a certain deadline and within a certain budget, and I want a certain completion ratio. So completion ratio says that of the total number of tasks, I want to complete k prime within that deadline and budget. Right? So that's my constraint. So what happens is, right, that when the data goes from here to here, the data has to wait in a queuing system on the cloud. Right? So that means that when I ship the data from here to here, if I ship the data, say, in 2 minutes, right, and the jobs have to wait here for another 2 minutes, right? The question is, can I use those 2 minutes that the jobs are waiting in the queue to do partial processing? Right? So the idea is, suppose that you can think of this analogy, right? Suppose you have to go from your home to your office, and then when you reach your office, you have to wait for 5 minutes before you're allowed to do something, right? So the question is that, why wait at the office? Why don't I use those 5 minutes that I would have waited at the office to do partial processing? So I delay my task, I delay my data transfer, so I can use those 5 minutes to do partial processing in the network, so that rather than wait here for 5 minutes, I can do 5 minutes worth of processing, and so when I hit the cloud, I can run immediately. Right? So I can use the delay, the waiting delay in the cloud to do partial processing in transit. And that's basically what we do. So we say, consider that there's some waiting time before a job can be executed. So the job is idle. It's not doing anything on the cloud. It's waiting in a queuing system in the destination node. So the question is, can I configure my data path from the source to the cloud so that I can use these in-transit resources to do processing before I hit the cloud? Okay, so we define it in this way. A little bit of maths, but not so much. So it's very simple maths. I'll take you through this. So what we are saying is we want to leverage this in-transit computation to minimize the amount of time a job is waiting at the destination in the cloud. And the objective of our problem can be defined as this problem. So we say PR is the number of resources in transit, and ER is the number execution on those resources. So just explaining that a little bit further. So what this says is I have PR in-transit resources. So PR is 2 in this case, and ER is the amount of execution I do on each resource. So what I want to do is I want to maximize the amount of processing I do, which is the number of resources PR multiplied by the execution time per resource. Right? So I want to maximize that value, which is PR times ER, which is this function here, subject to a set of constraints. Right? So these are the 4 constraints. So I say the constraints, so I want to maximize the total processing in transit, and I want to do it in such a way that the overall transfer time from my from the edge to the transfer time in the in-transit resources is less than the waiting time. So I want to make sure I use the waiting time. I want to do the whole processing within the job deadline. So the processing I do at the edge, the processing I do in the middle, in the in-transit nodes, the total data transfer, and the processing I do in the cloud, the total sum of that should be less than the deadline. I should do it within some budget, that budget constraints. And what this says is that of the total number of tasks that I want to run, remember I have k tasks, I want to make sure that I do k prime tasks to reach a certain accuracy metric. So C ratio is the completion ratio. So that means the total processing in the middle plus the processing in the cloud should be greater than my completion ratio to meet my accuracy target. Right? So now I have an optimization problem and I have a bunch of constraints. Now I can apply a whole bunch of multi-criteria optimization problem. I can use genetic algorithms, I can use simulated annealing, we can use heuristics, so we actually use heuristics here. So we can apply a whole bunch of heuristic mechanisms to solve this problem for cloud environments. And we've done this, and of course this is the total cost of doing this. So we have a paper here which explains this in much more detail. So essentially we built an infrastructure on Amazon which does this. So essentially we have the start node, which is my initial node. We have a bunch of in-transit nodes, and we have the cloud node. Each of these is emulated on a virtual machine in Amazon. And each of these is a virtual machine which runs a technique called GRE, which is generic routing encapsulation. What GRE allows us to do is to dynamically change the properties of these network links. So I can change it from, say, 2 megabits per second to 0.2 megabits per second. And we can use a GRE encapsulation, which, if you know networks, it uses a technique called token bucket filtering to change the properties on these network links. And we can use these properties to change the dynamics of our network. And within each node, we run this thing called SDN, which is a software-defined network controller in Python, which is called POX SDN. So a POX controller allows us to change the properties of each of these in-transit nodes. So this is our infrastructure that we use to simulate that behavior of that initial environment. Okay, so I have about 6 minutes, so I'll move on. So what we do is we use an Amazon. These are Amazon properties of. We use different virtual machine instances, and we want to have a completion rate of 60%. The completion ratio, our service level agreement, is to have a 60% completion ratio to meet these targets. So here are some results. I'll skip this part. So here's some interesting results, right? So what this shows is that the first graph here shows you, so what this shows you is I use a very high capacity virtual machine versus a very low capacity. So highest means a high capacity VM versus a low capacity VM. So what we are showing here is that you're using, so no in-transit means this is a traditional cloud. You do everything in the cloud. Whereas in-transit means you're utilizing cloud resources to a certain extent. So what you can see here is that we are the overhead of utilizing these resources. So that means we have more capacity now in the transit in the cloud. The cloud is now more idle because we're actually making more efficient use of our in-transit resources. So the gray bar tells you how much efficiently you're using these in-transit resources. And this tells you how much of the processing takes place in the cloud versus the processing in the middle within the network, right? So the traditional cloud, you're using everything in the cloud. Here you're using less of the cloud and using more of the in-transit nodes. Remember, the in-transit nodes have less capacity than the cloud, right? Because they're simpler resources. This is the more interesting graph. What we say is that by using more in-transit resources and given a certain deadline, we can actually achieve 100% completion ratio. We can actually accept more jobs because essentially we are using in-transit. So by using in-transit for the same price and the same deadline, and by combining the cloud data center, which is this, with in-transit, whereas a cloud could only complete about 80% or about 60 to 80% of the tasks, using in-transit resources, we can complete 100% with the same deadline and the same cost. Right? So that opens up the potential for having these new kinds of cloud environments, which are essentially use of network resources. So just in the last 2-3 minutes, I just want to, we have more results there, but you can read the paper. This shows you the cost. Who is making the money? So is a cloud vendor making the money, or is also the network provider making the money? So you can now share revenue. So here, between the cloud provider, so everybody's happy, right? Because the network providers, the telco vendors are making money because they're the middle providers, and the cloud guys are making money. So you can split split your happiness, right, between a whole bunch of different people. So that's another very interesting business model for doing this. Okay, so I'll just finish off just to show you where our research is leading to. Basically, so in the last 3 minutes, I just want to mention that one of the things we're using is something called approximations. So Energy Plus that I mentioned, the energy simulation software, is very compute intensive. You need a very large number of compute resources to run it. However, in many cases, you don't need very accurate results. You can get away with approximations, right? So there's a new emerging variety of techniques called Approximate Computing. There's a very interesting survey article where you can use a whole variety of strategies to reduce the accuracy, but still get a valid, accurate answer. So you can use precision scaling. You can say, I don't want, say, 5 decimal point accuracy. I'm happy to live with 3. You can use loop perforation. You can say, if my loop goes from I equals 1 to 10, I can say I equals 1 to 10 with a step of 2. So you do 1, 4, 1, 2, 4, 6. So you can you can do data dropping. You can do data sampling. You can use specialist hardware like specialist type of GPUs, which are inexact hardware. Or you can use neural networks, and which is what we have done. So what we do is we take Energy Plus simulation, and what we do is we run Energy Plus for a certain number of iterations, and then we collect the data from Energy Plus, and we use this to train a neural network as a function approximator. Right? So a neural network is approximating the behavior of Energy Plus. However, although neural network training takes a long time, neural network training can take of the order of minutes or hours. Once you have a trained neural network, a feed-forward neural network, the actual execution time is very limited, very, very small, right? So what we do is we take the Energy Plus simulation and we take the data output from Energy Plus and we train a neural network, and we use the trained neural network and we put it in the network, in transit, right? So we now have a Energy Plus running at the data center, and we have a trained neural network which is acting as an approximation of Energy Plus running on the edge and inside the network, right? So, and this paper describes that in more detail. We combine a more accurate model execution with approximate model using a trained neural network, and the trained neural network is now running in transit. And we have very interesting results where I'll just skip this part given the time. So what we now have is essentially this idea that we can have E+, which is our Energy Plus, and the trained neural network, the artificial neural network, working in combination, right, between the data center and the edge to be able to give us the same kind of output. But now, because we're using the Energy Plus, we have to make less use of our cloud, right? So using these approximate algorithms it's a very interesting way to combine both edge devices and data centers. Okay, so I'll finish here. I'll just conclude. So essentially, with big data and real-time data streaming, there's an emergence of a whole variety of data-driven and data-intensive applications. And there's a whole bunch of these applications, right? They range from surveillance with security cameras to sensor networks to cybersecurity. So there's a whole bunch of people interested in these big data applications. The question is, right, most of these big data applications rely on cloud infrastructure. And they try to ship the data from that, from basically the devices themselves into a back-end cloud platform. What we are saying is you don't need to do that. You need to rethink cloud for these kind of applications. So we need to rethink our cloud and data centers and integrate them with edge nodes, which are becoming more and more intelligent over time. So we say there's a potential for a new kind of providers to emerge to support revenue sharing in this new world of cloud and edge node integration. So we need to rethink our data analysis algorithm. So we need to, think of deep learning, right? If you take deep learning, in deep learning you have things like convolution or recurrent neural networks, which are very resource intensive, right? So a deep learning model is like a multi-layered neural network, which can be very, very resource intensive. Can you take a deep learning model? Here's a question for you, right? Here's a research challenge. Can you take a deep learning network and split it between a cloud and the edge? So you do partial learning in the network and do the rest of the learning at the data center. And how do you try to use that in comparison? So can data analysis be integrated across network edge and data centers? What additional modifications do we need to do algorithmically to take account of these new kinds of computer architectures? And how do we try to automate our application to make better use of all of this? And that's exactly 30 minutes. Thank you.
Thank you, Professor Omer, Rana. And I think we have a slot for one question, just one question. And thank you for your for being on time, for finishing this presentation on time. If you have a question.
Because I think eventually Amazon Lambda will support the talk that you did about creating your own execution model. And also I have 2 points to talk about is, should we have a limitation on the execution time inside the network? Because sometimes the energy cost for execution inside the network could be more than leaving everything to the cloud.
Yeah, so let me come to your two questions. So Amazon Lambda is a great example. Yeah. So Amazon Lambda, if you've not heard of, is a technique called serverless computing. So what you do is you don't pay for a virtual machine, but you pay for the execution of a function, often a Python function. So other vendors are jumping on the bandwagon. There's Google functions now. There's Microsoft Azure functions. There's a whole bunch of function-based approaches. The problem with those function-based models is you're still using them on the cloud. So if your last hop network is slow, right? Yeah. So although you're doing serverless computing on the cloud, if your last hop network is slow, your Amazon Lambda doesn't work, right? So the question, and actually that's a very interesting question. So one thing we are proposing with this osmotic computing is, can I ship a Lambda function to the edge? Yeah. So rather than run a Lambda function in the cloud, can I have a Python function which runs on lightweight containers, but is hosted at the edge device? Mm. And your second question was on?
Execution time inside the network, because you have to limit it somehow.
Absolutely. So many vendors are, so the question is, with many provisioning of networks and many 5G networks. So 5G means many things to many people. We probably will never get to 5G. We'll probably be 4.5G in the future. But the 5G vendors are saying essentially that they're able to host user functions inside the cloud. And that can be simple functions like taking data from one codec and mapping it into another codec, or taking a video sequence that's a high definition video and mapping it from high definition to QSIF or SIF format, or doing data sampling. So there's already a business model that many telco vendors are proposing to do that.
Can I ask one more?
Yeah, sure.
Do you think it's eventually will be application dependent? Because when you change the application, the whole model will change.
Absolutely. So that's why I put the first thing in. So this kind of work is really targeted towards streaming stream processing type applications,
Okay.
which are essentially driven with that deadline.
Can in the break, can I talk to you? Because currently I'm working the scientific workflow scheduling,
Sure.
but I would like to change the
Sure,
application.
happy to talk more.
Thank you.
Sure.
Sorry. Edward Ija? Okay. Edward.
Thank you, Dr. Omer. And now it's my pleasure to invite Dr. Arafat to recognize two key experts whose valuable support to our conference was really very helpful and make this conference very successful. Can I ask Dr. Saeed Al-Ghul to join us on the stage, please? Dr. Saeed, thank you for all the efforts you did for our conference, and yeah, we value this. Can I ask now Dr. George Dafolas to join us?
Other issues in the organizing of this really, we thank you a lot, Dr. Saeed. Dr. Saeed from Philadelphia University.
Now it's my pleasure to invite Dr. George to join us. We called his name this morning, but he was not there. Thank you for being keynote speaker in our conference. Okay, thank you everybody. And now it's session time. So there's two sessions. The first one is in room 1, which is next to this room. It's artificial intelligence, the topics. And the second session is computer and network security. It will be in Petra, which is opposite to this room. So can I ask you please to choose the session you want to join and go there. Thank you very much.